Hey folks, we want to talk about the fundamental counting principle in this section. Now, I want you to consider an example we've already looked at in the last section when we talked about listing all the possibilities for a particular situation, and we have one of those situations right here. So consider all the possibilities of three-digit numbers that can be made with the numbers 1, 2, and 3. Notice we need to know whether we can reuse the numbers or not, so I put in parentheses without reusing the digits. So remember what we did. The first thing we did is we say, okay, we're making a three-digit number, right? How many tasks is that? How many things do we have to do to build a three-digit number? Well, we have to pick the first number. There we go. Second number and third number. And blanks for doing this is going to be the way to go in a minute. But if we want to list all the possibilities, we need to talk about picking the first number. Now, if we're going to pick the first number, in how many ways can we do that? Well, we can use a 1, a 2, or a 3, right? So 1, 2, or 3. Now, the second thing we have to do is pick the second number. Now, when we pick the second number, if we can't reuse the digits, if I've already picked a 1, then the next thing I could do is pick a 2 or a 3. You with me? Now, if I've already picked a 2, then I could pick a 1 or a 3. And if I've already picked a 3, then I can pick a 1 or a 2. Right? So assume we've already picked a 1, so 2 and 3. You've already picked a 2, 1 and 3, already picked a 3, right? And for the third branch, then if I've picked a 1 and a 2 already, all that's left is 3. And if I've picked 1 and 3, then we need a 2. If I pick 2 and then 1, all that's left to pick is a 2, 2, 3, and then a 1, 3, 1 is 2, and 3, 2 is a 1. And we did this in the last video, so if you're struggling with this, please go back and watch it. Now, again, all the possibilities, well, we can list them. And remember, to list the possibility, you follow the branch. So I can go 1, and then 2, and then 3, and I will list that possibility as 1, 2, 3, or the number 123. Well, then I could follow this branch, 1, and then 3, and then 2, so I would list that possibility as 1, 3, 2. Then I could pick a different branch. How about 2, and then 1, and then 2? And so that'd be 2, 1, 2. I know you don't need me to continue to highlight this thing, but just to be sure you're comfortable with this, then I could pick a different color, pink. We hadn't used pink. 2, and then 3, and then 1. And I would list the outcome 2, 3, 1. I've only got 2 more outcomes to list, so might as well highlight them all, right? So the next one, let's go 3, and then 1, and then 2. So I would list 3, 1, 2, and then the only option left would be 3, and then 2, and then 1. Notice none of them are repeated, okay? And you've got 1, 2, 3, 4, 5, 6 different options. So how many possibilities? There's 6 possibilities. So if it asked you how many possibilities, you would just say 6. If it asked you to list the possibilities, this is what you would have to do. And a tree diagram or a table, if it applies, if you've got 3 tasks, a table's kind of challenging to do. But I'm all about a tree diagram because I think that gets you a long way. But I want to show you a trick real quick, and then I'm going to make the rule official shortly. But in this particular case, I want you to notice something. The first time in our first task, when we picked the first number, how many options did we have? Well, we could pick a 1, a 2, or a 3. So that's 3 different options. You could pick a 1, that's one of your options. You could pick a 2, that's the second option. You could pick 3, that's a third option. So there are 3 options for the first task. Notice I put a 3 in that blank. Well, how many options for the second task? Okay, so the second task, after you've already picked a number, notice there's only 2 numbers left in the pile. No matter which number you pick, there's only 2 numbers remaining that you can select from, no matter which one you pick. So you know what? You've got 2 ways to perform the second task. And then the third task, you know what? You only have 1 way to perform the third task. Why only 1 way? Why is that possible? because if you have three numbers, you had 3 the first time, and then you used one of them up, and then you have 2, and then you use that one up, and you only have one number left. Now watch this. If I multiply these 3 numbers together, 3 times 2 times 1 gives me 6. Notice that's the number of possibilities. So if you're ever asked to find the number of possibilities, you actually don't have to do a tree diagram to find out how many. The tree diagram is so we can find what the possibilities actually are. Okay? Now, I've got to show you one little thing, though. It's not quite as simple as this 3, 2, 1, but almost. Now, here's that, just in a more digital form, the same thing. Remember, the first digit, we had 3 to choose from. We could use 1, 2, or 3. The second digit, you had 2 numbers you could choose from, but that's off every branch. And the third time, we only have 1 number left that we could choose from, and there's our 6 possibilities right there. Now, it says this is considered uniform. This is a brand new word here. It's considered uniform if, or because, the number of ways to complete each task is not dependent on which choices were selected for the previous task. What in the world does that mean? Okay, so here's what's happening. Our first task, right, this doesn't matter. This uniform thing doesn't apply at all. It's when we move on to the second and third task. When I move on to the second task, notice there's 2 ways to do the task, no matter which was picked first. So this is saying, and that's called uniform because it's 2 ways every time. Like, for instance, if you picked a 1, that doesn't change the fact that there's 2 numbers over here to choose from. Say, what if you pick the 1 and then there's 3 options, but if you selected 2 first, there's only 2 ways to do the second task. That would mean it's not uniform. But if your second task does not depend at all on which of these 3 numbers you pick as to how many options you have left, then it's uniform. Notice the third task. No matter what, there's only 1 option for each branch. That's why it didn't branch at all. Okay? And no matter if you picked a 1 and then a 2, it doesn't change the number of options for the third digit. The third digit, you only have 1 choice, and that's it. So that's called uniform. And if you can say that your tasks are uniform, you can use that multiplication principle that I showed you just a minute ago, where I just multiply the number of ways to do the first thing times the number of ways to do the second thing times the number of ways to do the third thing. But before I make that official, let's look at another problem. All right, so what about the same example, but the numbers can be reused? So, for example, 332 is a possibility. Note what we just did, 332 is not a possibility because you can't use 3 twice. Or 222 is certainly not a possibility because you can't use 2 3 times. You wanted to use each digit just 1 time. Well, we could draw all this out. The fact is, I need to just direct you to the last video where we had a problem just like this. So your first branch is you could pick a 1 or 2 or a 3. The second branch, though, look at that. You could pick a 1, 2, 3, 1, 2, 3, 1, 2, 3, right? Because you're not limited at all after you've used the number. And then again, you could pick 1, 2, 3. Notice that first branch here is a 1 and then a 1 and then a 1. And we didn't have that possibility before. Now again, rather than trying to keep this all organized because you've seen it before, I'm just going to pop up the digital version of this, and there it is. Notice there's 27 possibilities. That's a bunch of possibilities. But the question is this uniform? Well, yeah, absolutely it's uniform. You know why? Because the second task, which is picking the second digit, is 3 options no matter what you picked first. If you picked a 1 first or a 2 first or a 3 first, it doesn't matter. You have 3 options after that. Now, it did matter when you couldn't, like when you picked a 1, when we couldn't reuse, you only had choices of 2 and 3 over here. So it doesn't mean that your choices are the same each time. It means the number of choices are the same each time. Does that make it more clear? Maybe it's more confusing. It took me a minute to think about what they mean by this. Now, since this is uniform, I'm going to tell you in just a minute, you can use the multiplication principle. Now, how many tasks I mean, to pick a 3-digit number, right, there's 3 tasks. You pick the first digit, you pick the second digit, and you pick the third digit, right? Well, how many ways could we pick the first digit? Well, remember, we're using the same numbers, 1, 2, and 3. I don't have it written in this problem, but that's all I'm allowed to use. So there's 3 ways to pick the first digit. Well, to pick the second digit, there's still 3 ways because we can reuse the number we picked first. To pick the third digit, there's still 3 ways because we can reuse either of these numbers. Now, if I multiply those 3 together, notice I get 27. Lo and behold, look at there. There's 27 possibilities. Now, again, this cute, lovely trick, which we're going to use a lot, will tell you how many possibilities, but it won't tell you what the possibilities are. So this factor tree still, or tree diagram, still applies. It's just only used to find the possibilities because there's an easier way often to find the number of possibilities. So let me make this official, this little cute little rule where we multiply these things together. And here it is. Not yet. The uniformity criterion for multiple part tasks. So this is that uniform thing first. It says a multiple part task is said to satisfy the uniformity criterion if the number of choices for any particular part is the same no matter which choices were selected for previous parts. Okay, now we have done problems really already in this first section that was not uniform. I don't know if you remember picking the stadium seats. So there were 4 people that went to a concert, but 2 people had to sit together. That is not uniform because it depends on what was selected first as to how many options you have for the next seat. Like the couple that had to sit together, if you selected the male part of that couple first, then the only option for the seat next to it was the female that had to be in the couple. But if you selected somebody else first, then you had choices for what sat next. You see what I mean? So it's different. But as long as you know it's uniform, then you could use this lovely rule right here, which is the fundamental counting principle. So notice it says when a task consists of k separate parts. So just like when we built a 3-digit number, we had 3 different tasks. The first digit, the second digit, the third digit. So that's what it means by k separate parts. And satisfies the uniformity criterion, which we just talked about. If the first part can be done in 1 ways, like an example in 3 ways, the second part can be done in 2 ways, remember if we weren't replacing, and so on, and the third part can be done in 1 way, or a K part, then the total number of ways to complete the task is given by the product. In other words, you just multiply all those numbers together. And that's when we got 6, and remember that's when we couldn't reuse a number. And then when we did the second problem where you could reuse the numbers, it was 3 times 3 times 3, which is 27 possibilities. So that's pretty much the rule we're going to use with a little bit of divergence here and there in this section. So let's keep doing some examples. You want to? So here's our example A. And I'm calling this officially example A instead of example C because those others were just to explain the principle. So now we're getting into the meaty part. So how many 2-digit numbers are there in our base 10 system of counting numbers? And we have a little hint here. It says, think about 40 is a 2-digit number, but 04 is not. Okay, why does that matter? Let's talk about it in a minute. First of all, to build a 2-digit number, what do you need? What information do you need to build a 2-digit number? Well, you need to know how many tasks there are, right? How many tasks to build a 2-digit number? How about 2? One of the tasks is picking the first number, and the other task is picking the second number. All right. Now, for our 2-digit number, this is where it gets fun. How many ways can we pick the first number? Okay, well, let's think about our options. It can't be 0. 0 cannot be a first number in a 2-digit number. So we could use the number 1, 2, 3, 4, 5, 6, 7, 8, or 9, right? How many numbers is that? That's 9 options. So we have 9 ways to pick the first digit. Well, how many ways do we have to pick the second digit? 9, right? No. Why is it not 9 ways to pick the second digit? Well, the second digit could be a 0, just like this example of 40. So you could use a 0, or 1, a 2, a 3, a 4, a 5, a 6, 7, 8, 9. Now, how many options is that? Well, you can count those numbers. That's 10 options. So I have 10 choices for the second number. Only 9 options for the first number, because I can't use 0, but 10 options for the second number. So how many 2-digit numbers are there? 90. Right? And when you count to 100, the first 10 of them, right? The first 10 of them are, if you count 0, are single-digit values. I guess if you're counting, you don't count 0. So there's only 99 2-digit numbers, or 99 numbers up to 99, but only 90 2-digit numbers. That makes perfectly good sense, don't you think? So, counting principle. Notice we didn't list them. We didn't start from 10 up to 99 and count how many numbers that was. We just used the multiplication principle. So let's try another one and see if we can use it again. So how many 3-digit numbers are there in our base 10 system of counting numbers? So very similar problem, except how many tasks do we have? Well, to build a 3-digit number, you got to pick the first number, you got to pick the second number, and you got to pick the third number. So there's 3 tasks. How many ways can we pick the first number? Well, I bet you're going to argue 9 ways, right? Because you can't use 0 again. So you can use a 1, a 2, a 3, a 4, all the way to a 9. That's 9 different options. But now the second number can be a 0, so there would be 10 options there. So 0 all the way through 9. That's 10 numbers if you count them. Can the third number be a 0? Of course it can. Like the number 900 is a 9 and a 0 and a 0. So there's 10 possibilities for that number too. So that's 10 options. Now, when I multiply those together, 9 times 10 is 90, and then 90 times 10 more is 900. So there are 900 3-digit numbers in our base 10 system of counting numbers. Now this time, I want to know how many 3-digit numbers are there that do not contain repeated digits. So y'all, I'm not allowed to reuse numbers. Okay? So again, a 3-digit number means, whoops, sorry about that flying question. 3-digit number means I need 3 tasks, right? I got to build the first number, I got to pick the second number, and I've got to pick the third number. Now, how many ways can we pick the first number? We know that there are 9 ways to pick the first number, because 0, not allowed, right? Now, how many ways to pick the second number? Well, right here, you picked a number 1 through 9, which means whatever number you picked, that number is out. So that means we have 8 choices, but you got to add 0 back in. So 8 choices plus 0. So 8 choices plus 0. How many choices is that? 9. Are you following this? Okay, the third number. Now the third number. Out of those 9 choices, which is 8 choices plus 0, we used one of those, and now we only have 8 options left to pick our number. Okay, then I multiply that together because that's what the multiplication principle says. And this is definitely uniform because the number of choices is fixed no matter what you pick in your first spot or what you pick in your second spot. So I multiply 9 times 9 times 8, and that gives me 648 3-digit numbers that do not reuse numbers. All right, and how many ways can an 8-member club elect a president and a secretary if no one may hold more than one office? Okay, what do you think? Okay, so what do we have to do? We have to elect, what are our tasks? We have to elect a president. Okay, there's the president task. We have to elect a secretary. There's our secretary task. And if you would like to label, you go right ahead. There we go, president, secretary. Now, in how many ways can we pick a president? Well, if there's 8 members in the club, I argue there are 8 different ways to select this president. Okay? All right, and then we've got to pick the secretary. Now, what does it say about the secretary? No one can hold more than one office. So the secretary cannot be the president also. So that means we don't have 8 people to pick from anymore, right? How many people are left to pick from? If we pick, Carly for president, then who's left for secretary? Well, there's 7 other people in the club, right? So 7. And when you multiply those together, because they are uniform, and most problems are, it takes an unusual problem, but we can make some that aren't. But 8 times 7 is 56. So there are 56 ways to select a president and a secretary from a club with 8 members. It's hard to believe there's that many options, right? But if you start pairing everybody up, when you have 8 people, you can see it'd be a whole lot of ways. So for example, E, I want to know how many non-repeating, very important, non-repeating, 4-digit counting numbers are there. So we're talking about counting numbers, which means the number can't start with 0. Non-repeating means if we use a number, we can't use it again. And of course, 4 digits tells us really how many tasks we have, right? So I've got my first task, my second task, my third task, and my 4th task. And if you want, the tasks do not have to be in a particular order. If you wanted to pick the 3rd number first and the 4th number second and the 1st number third, you could. Now, in this particular situation, it really doesn't matter at all, but I'm going to say it's the 1st number and then the 2nd number and then the 3rd number and the 4th number. Now, I'm going to go ahead and tell you a trick that I learned from the textbook, actually, that you put your most restrictive task first. So that if there were any restrictions or guidelines about how we were to pick this number, I would put that first. And actually, we kind of are. The most restricted is the fact that the first number can't be 0, right? So the first number, because it is a counting number, the number like 0, 1, 2, 3 doesn't count because that's 123 and that's not a 4-digit number. So the first number can't be 0. So what can the first number be? Well, if you think about what it can be, it can be, 1 or 2 or 3 or 4 or 5 or 6 or 7, 8 or 9. Any of those numbers. Now, how many choices is that? 1, 2, 3, 4, 5, 6, 7, 8, 9. That's 9 different choices. So we have 9 different ways we can pick that first number of our 4-digit numbers. Now, how many ways can we pick the second number? And something we need to think about along the way as we do this problem is what we picked here, does that affect the number that goes here? Well, for the second number, let's think about it. It is 0 is okay, right? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Any of those numbers is okay. If you count that, that's 10 numbers. But let's keep in mind, we can't repeat. What does that mean? We've got to throw one of these numbers out. Does it matter which one? It doesn't matter which one, right? We know that we picked one of these pink numbers, and we're going to throw that number out. So instead of having 10 choices now, we move one out for the pink one, and now we only have 9 choices here. Now, normally it steps down, right? If you're not repeating, it'd be 9, then 8, then 7, then 6. But the reason this is 9 and then 9 again is because we added 0 back into the mix. You with me? All right, for the third choice, what numbers can we pick? Well, we can use 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Any of those numbers would be fine, except we can't use either of these 2 numbers that we've already used. We've used 2 numbers that are on this list. Which 2 numbers? We don't know. We actually don't have to know to pick this selection, but we know with 2 of them gone, 10 minus 2, that gives us 8 possibilities for the third one. And then for the last number in line, we have choices of the numbers 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Once again, that is 10 numbers. But you know what? We've already used 3 of those numbers, 3 different values. We've already used 3. If we subtract out the 3 we've already used, that's a 3. That gives us 7. Now, the multiplication principle says we just multiply these values together because we pick the first number and the second number and the third number and the fourth number. And if you find that you say and between your selections, then you know it's multiplication. Okay, so we said we had to pick the first number and the second and the third and the fourth, so I know I multiply these together. And so far, that's all we've learned anyway, is multiplication. Another thing we have to keep in mind is this uniform? Does it matter what number selected here as to how many choices I have here? And at first you think, well, yes, right? Because we pulled one out, which means we have one less option. We just added 0 in. But it doesn't matter which number. Like if I picked a 3, do we have 9? If I picked a 1, do we have 9? Do you see what I mean? So it doesn't matter which number we pick. No matter what, we're going to have 9. Where it would not be uniform is if we picked one number and we would have a different number of choices than if we picked another number. And trust me, I realize that can be confusing. I have an example coming up shortly that's not uniform, just so you can see what I'm talking about. And if it's not uniform, you know what? We can't multiply the numbers together. You'd have to use a different technique. But anyway, let's get to this big old number multiplied out. So 9 times 9 times 8 times 7. When I do that work, I get 4,536. Can you imagine listing all those? Me either. Okay, so we know how many choices we have. We really don't want to list the choices, right? Even 9987 is one of those 4,536 choices. Okay, now let's go on to another problem that's very similar to this one. Okay, so notice I put like E. This is very similar to E. I didn't call it F, I just called it like E. But if you'd like to call it F and then change all the rest of the problems in the lecture, you certainly can. Now, a problem like E, it says how many non-repeating, there we go again with the non-repeating, odd 4-digit counting numbers are there. And you know what odd numbers are? Odd numbers end in 1, 3, 5, 7, or 9. Now that's just the fourth digit. What's in the first, second, or third digit place does not matter. What's in the fourth place is what matters. And to make it odd, again, it ends in 1, 3, 5, 7, or 9. Now, at first thought, you might just think half of the numbers are even and half of the numbers are odd. If you thought that, don't feel bad, because I did too. At first thought, I thought, why don't we just take the answer we got before? There you are, 4,536, and just cut it in half. Because half of these numbers ought to be even and half of these numbers ought to be odd. Well, it turns out it's not as simple as that. Because when you look at this list of numbers, 4,536, we don't have the list in front of us, do it. When you look at the amount of these and you think about particular number. Matter of fact, you know what? I told you that the number 9,987 would be in this list. No, it won't. You know why? Because 99 can't be in the list. None of the numbers can match. So this list does not include numbers like 7,000. Let me get my pen working. Numbers like 7,735 or 6,146 or 2,222. All those numbers are out. Why? Because they have repeating values, right? And that messes up the fact that half of my numbers are even and half of my numbers are odd. You ought to think, well, even the ones you throw out, it ought to work out that half of them are even and half of them are odd. No, you can't do that. So it doesn't work that way when you're doing non-repeating. Now, if you were doing repeating, I think you could argue the fact that half of the numbers are even and half of the numbers are odd. Or about half, but that would be a completely different problem. So don't think when it says odd or even, you can just throw half of them out, because it depends on the conditions that you start with. And so let's go back and address the problem that we have. Now, remember how I mentioned a hint? You put your biggest restriction first. The fact that the fourth place should be odd, that's the biggest restriction that we have in selecting our values, so I'm going to put that first. Now, how many tasks do we have? We know we have 4 tasks again, because it's a 4-digit number. So we have a task 1, task 2, task 3, task 4. And again, in the last problem, we picked the first number was the first task, the second number was the second task, the third was the third task, and so on. But this time, the most restrictive is the fourth digit. That fourth digit, let's put it first. This is the fourth digit. And then we have another restriction on the first digit. So then I'm going to put the first digit, and then the second, and then the third. Okay? By the way, I tried it the other way, and it didn't work. You know why? Because it wasn't uniform. All right? So let's do this, and then we'll talk about the idea of not being uniform. So if the fourth digit goes first, now tell me, it has to be odd, right? So what numbers can we have here? Well, how about a 1, a 3, a 5, a 7, or a 9? You agree? 1, 3, 5, 7, and 9. That's the only options for the fourth digit to make this 4-digit number odd. All right, so how many choices is that? That's 5 choices. So I have 5 ways I can pick the fourth digit. Now let's move on to the first digit. So what's the restriction about the first digit? Remember, I told you there was a restriction on it. Do you remember what that was? Well, it's a counting number, and counting numbers can't start with 0. So our first digit cannot be 0. So we can choose from 1, 2, 3, 4, 5, 6, 7, 8, and 9. Those are all the numbers that we can choose from. Now, how many is that? That's 9. But now wait, this is non-repeating. So if it's non-repeating, we've got to take out the number that we've already selected. We don't know if it's a 1, 3, 5, 7, or a 9, but it's one of those. If you take that number out of this list, then you have 8 numbers to choose from. Uh-oh, I forgot something. Is that right? You know what I forgot to do? Do you see it? Oh, yeah, no, it's right, it's right. I thought I forgot 0. I didn't forget 0. 0 can't be the first number. We're good, okay? Now, the second digit. What's up with the second digit? Well, it can be any number including 0. So it could be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. It can be any of those numbers, which is 10 choices. But the deal is we've already used 2 numbers up, right? We used 2 numbers up for the fourth place, and we used we used 1 number up for the fourth place and 1 number up for the first place, which leaves us 2 out the window. If I throw out 2, then I have 8 possibilities for my second digit. Now, why are these the same when usually it steps down? Because we added 0 back in. So I took that 8 down to 7, but I added the option of 0 back in, which made it 8. And now the third position. What can we do with the third position? Well, what numbers can it be? The third position can be a 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Don't feel like you have to write all these down. I'm just trying to make it very clear, which is 10 options. But how many numbers have we already used up? 3, right? We used up a number here, we used up a number here, we used up a number here, and now we used up a third number. Well, we're using a fourth one now, but we've used 3 already. 10 minus 3 is 7. So how many non-repeating, odd, 4-digit counting numbers are there? Well, whatever this is, 5 times 8 times 8 times 7. And that gives me 2,240. 2,240 odd 4-digit counting numbers. Now for the last problem I want to do in part 1 of the video, I've got more examples for you in part 2, but in part 1 of the video I call extra. Why? Because really I didn't even want to throw it in, but it's something I need to talk to you about because it threw me a little bit for a loop and I want you to see it as well. So notice what I'm asking, how many important things non-repeating, let me get my pen working, you keep reading, how many non-repeating, even 3-digit counting numbers are there? Even the counting numbers is important, right? Counting numbers means the first can't be 0. Non-repeating means we got to take the number out each time so we have less choices the next time. Even means it ends in an even number, right? 0, 2, 4, 6, 8. And 3-digit, that's how many tasks we have. So we have 3 tasks. Task 1, task 2, task 3. Now remember, the most important thing that I've probably told you past uniform and multiply these choices together, or these options together, is the idea, it's a trick, that your most restrictive choice needs to come first. The order you multiply in, you know that doesn't matter. So it's not like you have to pick your first digit before you pick your third digit. Now, it is definitely the third digit that's the most restrictive. Why? Because it has to be an even number. And then the next most restrictive thing I would say is the first digit, because remember the first digit can't equal 0. And then you could pick the second digit last, which has no restrictions other than the non-repeating situation. Okay? So if we're going to pick the third number first, it's an even number, okay? Then it can either be 0, 2, 4, 6, 8. Now, how many choices is that? That's 5 choices. So in that spot, of course, I put a 5 to represent the 5 possibilities of my third number. If I'm counting even numbers, then it could only end in 0, 2, 4, 6, 8, and that's it. Okay? Now my first choice right here is it can't equal 0. So I have choices of 1, 2, 3, 4, 5, 6, 7, 8, 9. How many choices is that? We couldn't include 0, right? That's 9, right? But, we've used up one of these numbers. Okay? Now, here's where it gets weird. Okay? We have 9 choices. We've used up one of these numbers, and so now 9 turns into 8. Maybe. The question is, it does if one of these 2, 4, 6, or 8, if one of those was our choice that we picked. But it's different if 0 was picked. So let me explain and maybe use a different color pen just real quick. I don't know if it's going to help you or not. I've just messed everything up because I erased my 2. There we go. Okay. Now, if we selected 0, right? If 0 was our third number that we picked, which makes even numbers, right? If we selected 0, then we would have 9 choices. 1, 2, 3, 4, 5, 6, 7, 8, 9. On the other hand, if we selected 2, 4, 6, or 8, we would have to mark off whichever number that was, 2, 4, 6, or 8, and we would be left with 8 choices. Now here's the problem. That's not uniform. And whenever you have a situation that's not uniform, you can't use the multiplication principle. Now there are ways you can break it down where you're doing 2 separate calculations or more to handle your issue. But all we know right now is the multiplication principle. And since this is not uniform, right now we can't calculate this. Now, you can certainly write them all down and tell me how many there were, but we don't have the skills. Just it's not a basic problem. There's a little bit more to it. And so I decided to leave this in here to show you that if this is an odd question, if it says how many odd 3-digit, 2-digit, 4-digit like we did numbers, there's no problem with setting this up as long as you put your most restrictive choice first. But if I all of a sudden change this to an even problem, then it changes things because the first digit can't be 0. And one of the selections for an even number is 0. Therefore, it means you don't have a uniform situation. I hope that didn't super confuse you. We're going to try to keep it simple here, but I needed to explain that because it's just not as simple as taking the total and dividing it by 2 to get even or odd, or not as simple as an even problem just works just like the odd problem. And I had to find out that the hard way too. So just something to think about. If you have any questions, of course, let me know and come back for part 2 where we do more examples. Don't worry, they don't get harder. They're just different. You have a great day.